Okay, so in this part of video, we will discuss, or I will show you the how we can analyze the Zener diode circuit. Okay, let's consider this circuit. So we have the supply voltage is 12 volt, and we have resistor 2 kilo ohm, and we have here is you have the Zener diode. This Vz is equal to 6 volt, and Z minimum is equal to 0.1 milliampere. Okay, Z minimum Z minimum, in the previous slide we have the term called Izk. So the knee voltage, the Zener current at the knee voltage. So this is actually almost the same. It's the similar symbol. Izk means Izk. So let's say this is given. Izk minimum is 0.1 milliampere. Okay, the question is solve for the V out and Izk. So how much is V out and Izk? Izk is current that pass through the or cross the Zener diode. Okay, so then you need to notice that here the V out is not connected to any component, so this is open circuit. So the current here is 0, so this is 0 ampere. Thus, the current at the R will be equal to Izk. Okay, so how we can solve this circuit or solve the problem is we need to do the DC analysis. Okay, so for DC analysis of diode, you can use the equivalent model. So for Zener diode, usually we use the ideal model. So the Zener will be replaced by the battery, so equal to the 6 volt. So here you can redraw this one. This 6 volt, this is positive 12 volt, this is 2 kilo ohm, and then at the middle we measure the V out. Okay, so this is you should have this circuit after you replace the diode with the battery of 6 volt. So now you can get the value of V out. Okay, you can get the value is V out is equal to, very simple, equal to 6 volt. Okay, and then you can calculate the Izk. So Izk, okay, there's many way how you can calculate the Izk. Let's say we want to let's say I want to do the KVL. Okay, from plus 12 volt until ground, so it should be minus 12 plus Izk 2k, and then this one is plus 6, so equal to 0. So here Izk is equal to 12 minus 6 over 2, so this is equal to 3 milliampere. Okay, so the Izk, the Zener current is 3 milliampere. Okay, based on the calculated Izk, Zener diode operate as a regulator or not? So remember that where if the diode is on, means that the diode have significant current value. So 3 milliampere is quite high. So Izk is higher than Izk min. So this is 3 milliampere higher than 0.1 milliampere. So means that the current is there. So Zener diode is on. So yes, the diode operate as voltage regulator. So this is the analysis. Okay, so now at the V out we connect the V out is connected with the load, okay, RL. So the V out is not an open circuit, so V out is across the load. So as the load resistor get larger, so what will happen to the V out? So now the V out is the voltage across the RL. So the voltage will be depend on how much the current of IRL. So how much the current of IRL? So it will depend on how much the current of IZ. So because we have the two current paths, or we call it two junction here. You have the current from the resistance of R is divided into IZ or IRL. So this current will depend on the value of RL, of course, and the value of R. So as the load resistor get larger, the load current decrease. So when the load resistor get larger, this is higher, the load current decrease. So this is why, because of, if you want to derive the equation for V out, so V out using the Ohm's law, V out equal to IRL times RL. Okay, and then you should get IRL equal to V out over RL. Okay, so here V out is in parallel with the VZ. So here this is a VZ. So V out is in parallel with VZ. So the parallel circuit, the voltage is same. So lastly, you should get IRL equal to VZ over RL. Okay, so this is fixed value. So when the load is higher, IR will become lower, decrease. So more current burning through the Zener. So when IR decrease, what happened? When IR decrease, much of the current will go through the Zener. So more current burning through the Zener, putting the diode deeper into the breakdown. Okay. As load resistor gets smaller, what if the load resistor gets smaller? So when load resistor gets smaller, the load current increase. Okay, load current increase. When load current increase, much current is drawn to the RL, so there will be less current across the Zener. Okay, so what happened? Less current burning through the Zener. So and then there will be some possibility that the Zener will operate near the minimum, what we call it, the VZK. Okay, the new voltage of the Zener diode. Okay, this analysis show that the changes in R resistor, R and RL, will affect the operation of Zener as voltage regulator. Okay, when we have the load connected to the load in parallel with the Zener diode, the common approach, the common way to analyze the circuit is by using the Taverning Theorem. So this circuit can be redrawn something like this, and then the position of RL and Zener can be switched because this is in parallel. So this is no different whether the Zener at the left or Zener at the right, as long as it maintain the parallel connection. So here, this the part labeled by this dash line can be simplified using the Thevenin Theorem. Okay, after the Thevenin Theorem, you will have only one DC source and one resistor, so VTH and RTH. So what is the general equation for VTH. VTH is equal to, we use the voltage divider across the RL. So we have VTH equal RL over RL plus RS times Vs. So this is VTH. And how about RTH? RTH is Thevenin resistance. Thevenin resistance is considered by replacing the positive DC voltage with the ground, and then we see the resistance from this point. This is RTH, and from this point RL and RS in parallel, so RS parallel with RL. So the equation is RS times RL over RS plus RL. So this is general equation that will be used when you are using the Taverning theorem. Okay, in the DC analysis, you use Taverning theorem, and at some point you can calculate the Zener current, YSAG. Okay, Zener current. So the Zener current is very important. The analysis of Zener current is very important in order to ensure that the Zener diode operates properly as a regulator without any damage. So the condition for the YSAG must be higher than YSAG mean, the minimum YSAG. So if YSAG is lower than YSAG means that means that the diode is at off state. So it's off state. It's not operate. It's not turn on. It's at off state. However, the Zener diode need to be maintained below the maximum current value. This is called YSAG max. And how the YSAG max can be determined or can be calculated is by using the PD max, power dissipation maximum power dissipation.